Hello and welcome. Tonight we're going to face a disturbing mystery that fiction almost always ignores, but that can send a chill down your spine just by thinking about it. Have you ever stopped to consider that the greatest risk of an alien invasion might not come from intelligent beings, but from something completely invisible? That single question changes the way we look up at the sky. Did you know that while we watch the cosmos expecting gigantic spacecraft, the real threat could be microscopic, traveling silently through the vacuum right now without anyone noticing? The distance between the stars is immense, but time favors what is invisible. Could the true arrival of another world come not as an explosive event, but as a subtle biological contact for which our bodies have no defense? Tonight we'll explore the resilience of extremophiles and the theory of panspermia, looking at real scientific ideas that challenge our assumptions about how fragile life truly is. We'll walk through a scenario where the threat is microscopic and consider how our own biology might react to a visitor we cannot see, cannot communicate with, and cannot negotiate with. Before we continue, there's a small way you can support the work here at Cosmos for Rest. If this topic sparks your curiosity, consider leaving a like and subscribing so you don't miss future explorations of the universe. These simple interactions help thoughtful science content continue reaching people who enjoy learning while they relax. Now, settle in, close your eyes, and let science guide you. Let's begin this journey by looking upward. Imagine for a moment that you are standing in an open field, far from the lights of the city on one of those nights when the sky seems to press down on us with its sheer immensity. The darkness is dotted with thousands of stars, and every point of light is a quiet reminder that we are not isolated in a closed room, but drifting in an infinite and unknown ocean. Since humanity first learned to look at those stars and understand that they were other suns, we have carried an ancient question, etched deep into our curiosity. Is there someone out there looking back at us? And if they ever came here, what would that meeting be like? For decades, our imagination has been trained to expect a spectacle. Books, films, and stories have taught us to fear the noise. In our minds, we built the image of an alien invasion as a grand event, full of sound and fury. We expect gigantic metallic ships tearing through the clouds, blocking out the sun and casting enormous shadows over our cities. We imagine beams of light, incomprehensible technologies, global communications failing, and perhaps a humanoid figure descending from a ramp to demand our surrender or offer a doubtful peace. We project our own human behaviors onto the universe: war, conquest, diplomacy, negotiation. We assume that the other, if it comes, will come with intention, with a plan, with a mind we can try to understand or fight. But the universe rarely behaves like our fiction. Nature, even here on Earth, teaches us that the most efficient and devastating invasions do not arrive with trumpets and explosions. Think of the silence of a forest. The struggle for life happens there every moment, yet it is quiet. The fungus spreading through the roots of an ancient tree does not announce its arrival. The virus that jumps from one species to another does not deliver a declaration of war. They simply exist, persist, and multiply. And what if we apply that same cold, efficient biological logic to the vastness of space? The scenario we are about to imagine together is very different from an action movie. It is a scenario of absolute silence. Imagine that contact has already begun, or that it is about to happen, without a single ship appearing on radar. Space is far too vast for rapid travel by large fleets. The energy required to move metal and complex crews between the stars is enormous, nearly impossible, according to what we currently understand about physics. But life is small. Life is stubborn. The most efficient package for transporting information and biology across the cosmos is not a starship the size of a city. It is a spore, a bacterium, a fragment of genetic code protected by a microscopic shell, drifting along gravitational currents, hitchhiking on comet dust, or hidden inside the frozen heart of an asteroid. That shift in perspective is what makes this mystery so fascinating and, at the same time, so unsettling. We are watching the sky with enormous radio telescopes, listening to radio frequencies, searching for mathematical patterns that might signal intelligence. We are searching for civilizations. But perhaps the greatest risk is not a civilization at all. Perhaps the visitor is not a who but a what. Not a strategist general but a cosmic seed that purely by chance found fertile soil called Earth. Imagine the arrival. There would be no Independence Day, no panic in the streets, at least not in the beginning. It would be an ordinary day, perhaps a beautiful meteor shower streaking across the early morning sky, burning through the atmosphere. Most of us would make a wish when seeing a shooting star, never imagining that within the dust left behind by that burn, or within a fragment of rock falling quietly into the ocean or a remote forest, something survived. Something that had been sleeping in the cold vacuum of space for millions of years, and that now, sensing the warmth and liquid water of our world, begins to awaken. In this hypothetical scenario, the invasion is not an act of malice. It is an act of biology. That organism does not hate us. It does not even know we exist. It simply does what life does best. It finds resources and replicates. And it is precisely that indifference that defines our thought experiment tonight. An intelligent enemy can be reasoned with, deceived, negotiated with. But how do you negotiate with a colony of microorganisms obeying nothing more than a blind biological imperative? How do you ask for peace from something that has no concept of peace? The history of science shows us that the greatest paradigm shifts often come from what we cannot see. Before the invention of the microscope, humanity lived surrounded by an invisible world of bacteria and viruses, blaming disease on bad air or divine punishment. We were vulnerable because we were ignorant of the microscopic scale. Today, we may be looking at space with a similar innocence. We see the large, the bright, the visible, but the space between the stars is not empty. It is filled with dust, gas, and complex organic chemistry. The idea that life could travel between worlds, a theory known as Panspermia, which we will explore more deeply later, suggests that Earth may not be an isolated bubble. Instead, it may be part of a cosmic archipelago, where the pollen of stars occasionally drifts from one island to another. So as you relax now and allow your mind to wander through this possibility, try to erase the image of little green men or conquering robots. The true stranger may be far simpler and far stranger. It may have no face, no eyes, no voice. It may be a form of life based on a chemistry our scientists would need years to decipher, and its arrival would be as subtle as the wind that carries desert dust across an ocean and settles it quietly on cars in a distant city. We prepare ourselves for wars among the stars. We build defenses. We write protocols for intelligent contact. But our biology, this extraordinary and complex machine that is the human body, evolved in protective isolation here on Earth. We learn to live with and fight against the microorganisms of this planet. Our immune system is a library of memories from ancient battles fought here. But what happens when the library has no record of the invader? What happens when the biological key arriving from space fits none of our known locks? That is where the mystery deepens. This is not about claiming that such an event will happen, or that it is happening now. It is about expanding our understanding of what is possible. When we shift our focus away from the loud spectacle of science fiction and place the lens on the quiet science of astrobiology, we discover that the universe may be far more creative and potentially far more dangerous than our screenwriters ever imagined. The concept of an invisible invasion forces us into humility. It reminds us that despite all our technology and pride, we are still biological organisms living inside a delicate biosphere, exposed to the silent winds of the stars. As we continue this journey, keep this image in mind: the fragility of life against the vastness of the inanimate universe, the contrast between our desire for control and the random chaos of the cosmos. We will walk along that thin line where science meets imagination, exploring how life, in its simplest and most resilient form, might be the true protagonist of an extraterrestrial encounter. And what if somewhere in that immense darkness, a microscopic hitchhiker is already on its way, not out of malice, but simply because the universe is a place of constant motion? Take a slow breath. And let's continue this investigation. Now let's take an inverse journey. Let's turn our gaze away from the dark immensity of the star-filled sky, where we imagine that wandering cosmic dust, and instead look inward. To understand the true risk of a biological encounter with the unknown, we must first understand the remarkable fortress we inhabit, the human body. While you rest now, breathing calmly, body still and relaxed, an entire universe of activity is unfolding inside you, a silent, tireless, ancient activity. In essence, We are a planet for trillions of tiny inhabitants. Our cells, our bacteria, our chemical processes form an ecosystem as complex as a tropical forest or a deep ocean. And just like the Earth itself, the human body has borders, defenses, and an army dedicated to maintaining order. That army is the immune system. It decides who enters and who stays. It patrols every blood vessel, every tissue, every centimeter of our biology, asking a single fundamental question of everything it encounters: do you belong here? To understand the mystery of an invisible invasion, we must understand how this defense was built. It did not appear overnight. Your immune system is the result of a story billions of years long. It is an inheritance. Every one of your ancestors, from the first unicellular organisms drifting in Earth's primitive oceans to modern humans, survived attacks. They survived viruses, bacteria, fungi, and parasites that tried to turn their bodies into homes. Those who survived passed their genetic memory forward. Today, that memory lives inside you. You carry in your blood the wisdom of countless ancient battles. Scientists call this process co-evolution. It is a slow and dangerous dance between us and the microorganisms of Earth. As viruses evolve new ways to enter our cells, our bodies evolve new ways to lock the doors. It is a biological arms race that never truly ends, but it creates a certain familiarity. We know our enemies. Even when a new virus appears on Earth, it is still built from the same ingredients. It uses the same biological alphabet. It follows the same basic rules of life that we do. It is, in a strange sense, still a neighbor, even if it is an unwelcome one. Imagine your immune system as an immense library filled with ancient books and strategy manuals. When you catch a cold, or when your skin becomes inflamed after a small cut, the sentinels of your body rush to that library. They search the records for a way to deal with the invader. They identify shapes, proteins, and chemical structures that reveal the enemy. "Ah, I recognize this pattern," the defense cell might say, and then it produces the right weapon, the precise antibody capable of neutralizing the threat. It is an elegant system, a brutal one, but incredibly efficient. Yet here lies the heart of our mystery, the place where biology meets cosmic speculation. That entire library, every page, every strategy, every memory, was written in only one context: Earth. Your body is an expert at fighting life from Earth. It understands DNA, RNA, and proteins, built from the 20 amino acids that form life on this planet. We are perfectly adapted to our home. But what happens when the visitor does not come from this home? Let us imagine, purely as a scientific hypothesis, that the cosmic dust we spoke about earlier carries a microorganism from another world. An organism that evolved on a planet with different chemistry, under the light of a different star. It never participated in our evolutionary dance. It did not spend the last 3 billion years learning the rules of the game here. It is an absolute stranger. When this hypothetical organism comes into contact with human biology, two fascinating and unsettling scenarios might unfold. Both arise from the same problem: failure of recognition. The first scenario is total invisibility. Your immune system works like a security system that searches for specific keys. It scans for shapes and structures that signal danger. But if alien biology is fundamentally different, if the cell wall of this microbe were made of silicon instead of carbon, or if its proteins had geometries that do not exist on Earth, our sentinels might simply fail to see it. To the immune system, that invader might appear as harmless as a grain of sand or a microscopic piece of plastic. The alarm never triggers. There is no fever, no inflammation, no cough. And in the quiet of that ignorance, the invader might begin to act. If it finds something inside our cells that it can use, sugar, water, heat, minerals, it could begin multiplying freely, facing no resistance at all. It would be a silent invasion in the most literal sense. The body would be colonized without ever fighting back, because it never realized it was under attack. By the time symptoms appeared, they might not resemble the symptoms of a battle, like fever, but rather the symptoms of exhaustion. A slow depletion of vital resources stolen by guests who were never invited. The second scenario is the opposite, but just as dangerous. Sometimes the immune system encounters something it cannot classify and reacts with panic. Without clear instructions in its ancestral library, it may decide to attack everything around it. This happens in certain diseases we already know, where the body's own defenses cause more damage than the original problem. Faced with an unknown alien protein, the human body might unleash such a violent storm of chemical defenses that the system itself collapses. The invader would be only the trigger. Our own biology would become the weapon. This reflection invites us to look at our own history with greater humility. We already know what happens when isolated human populations meet for the first time. When explorers crossed oceans and encountered societies that had lived in isolation for thousands of years, the biological meeting was often tragic. Common germs for one group became devastating plagues for another, not because those pathogens were especially powerful, but because there was no immune memory. Now expand that scenario to the scale of the universe. The distance between two continents on Earth is insignificant compared to the distance between two planets. The biological isolation between Earth and any other world has been absolute since the beginning of time. Biology is a science of keys and locks. Life on Earth shares the same keys. We can eat plants and animals because chemically we are compatible with them. A virus from a bat can infect a human because deep down we are distant relatives. Mammals with the same basic cellular architecture. But an organism from Mars, or from a moon of Jupiter, or from a distant exoplanet, that organism is not our relative. It does not share our evolutionary tree. It is the true definition of alien. And that fundamental difference is what makes prediction so difficult. It may be that our biochemistry is so incompatible that nothing happens at all. The alien microbe might fall into our lungs and die instantly, unable to survive our oxygen or our temperature. That is a real and comforting possibility. Perhaps we are toxic to them, just as they might be toxic to us. Incompatibility could be our greatest protection. But science teaches us not to rely only on luck. Immunology shows us that life is opportunistic. It finds pathways. On Earth, bacteria have learned to eat plastic. They have learned to survive inside nuclear reactors. They have learned to resist antibiotics that never existed in nature. The flexibility of life is enormous. And that is why the question persists. If life out there is as stubborn and adaptable as life here, what would stop it from learning how to use us as hosts? As you keep your eyes closed, imagining these tiny invisible battles, think about the extraordinary complexity that keeps you alive right now. Your heart pumping, your blood circulating, your cells quietly patrolling the borders of your body. You are an evolved fortress, but even the strongest fortress may have walls that can be climbed by those who arrive carrying entirely new tools. Understanding that we are not universal, that we are simply terrestrial, is an important step in this journey. Our biology is a perfect answer to the questions asked by Earth, but the universe may ask different questions. And to understand what kind of life could survive the journey through space, to reach us and test our defenses, we must leave the human body behind and travel to the most hostile places on our own planet. We must meet the masters of survival, those that live where nothing should live. To truly understand the scale of a biological risk coming from the stars, we need to abandon for a moment the comforting idea that life is fragile. We, human beings, are fragile. Our existence depends on a very narrow range of conditions. We need mild temperatures, a specific atmospheric pressure, abundant liquid water, and protection from intense radiation. If any of those conditions change drastically, we perish. For a long time, science believed this fragility was a universal rule. We assumed life could only exist in the so-called habitable zone, that delicate region around a star where everything is balanced and gentle. But our own planet eventually taught us that we were wrong. Before we search for strange life on Mars or on the icy moons of Jupiter, we need to look at the strange life that already exists here on Earth. These organisms are not monstrous because of how they look. They are monstrous because of how incredibly resistant they are. They are called extremophiles, organisms that thrive in the extreme. They prove that biology does not need comfort to flourish. It only needs opportunity. Imagine descending now to the deepest parts of Earth's oceans. We are speaking of abysses where sunlight has never arrived, kilometers beneath the surface. The pressure of the water there is so immense, it could crush a steel submarine like a soda can. The temperature swings between near-freezing darkness and the infernal heat of hydrothermal vents, where water erupts from the crust of the planet, loaded with toxic metals and sulfur. For decades, scientists believed these places were sterile deserts. But when the lights of our deep-sea submersibles illuminated those depths, we found life. entire ecosystems thriving in total darkness, bacteria that do not depend on sunlight, bacteria that feed on poisonous chemicals, transforming heat and minerals into energy. They live on the edges of underwater volcanoes, in conditions that would kill a human in seconds. These organisms teach us the first important lesson for our imagined scenario. Life does not need a planet like Earth to exist. It can exist in what we would call hell. That means worlds we consider dead, too hot, too toxic, too pressurized, may actually be home to organisms that would find our environment almost comfortable. Now let's move from heat to cold. Picture the white, silent plains of Antarctica. Beneath kilometers of solid ice lie lakes that have been sealed off from the outside world for millions of years. One example is Lake Vostok. This environment is one of eternal darkness, extreme cold, and complete isolation. And yet signs suggest life exists there. Microorganisms that either entered a state of suspension or evolved to metabolize scarce resources at a glacial pace. They teach us the second lesson: patience. Life can wait. It does not need constant activity. It can sleep for ages, waiting for the right moment to awaken. But perhaps the most unsettling example for our reflection about space comes from a tiny animal, almost invisible, that may live in the moss of your own backyard. The tardigrade, also known as the water bear. This tiny creature with 8 legs challenges almost everything we know about mortality. When conditions become hostile, when water disappears, when temperatures rise or fall dramatically, the tardigrade does not die. It transforms. It shrinks. It expels nearly all the water from its body and enters a state called cryptobiosis. In that state, it becomes something like a grain of biological glass, and in that form, it is nearly indestructible. You can boil a tardigrade, and it survives. You can freeze it close to absolute zero, the temperature where atoms almost stop moving, and it survives. You can expose it to pressures greater than those at the deepest ocean trenches, and it survives. But the most astonishing fact of all is this: we have already taken tardigrades into space. Scientists expose them directly to the vacuum of space, without air, and to cosmic radiation that would shred the DNA of a human being. When those tardigrades were brought back to Earth and rehydrated, they simply woke up. They resumed their lives as if nothing had happened. Some even reproduced. That discovery changed the way scientists think about life in the universe. The tardigrade proves that a terrestrial organism can survive the journey through space without a spacecraft. It does not need life support. It does not need shielding. It is its own spacesuit. Now ask the uncomfortable question. If Earth, a relatively gentle planet, produced a creature capable of surviving the vacuum of space, what might a truly hostile planet produce? Imagine a world where radiation is 1,000 times stronger than here. Any organism evolving there would not merely tolerate radiation, it would be armored against it. And we already have a hint of such resilience here on Earth, a bacterium called Deinococcus radiodurans. This microorganism can survive doses of radiation that would kill almost any other known life form. Its secret is extraordinary. Instead of avoiding damage, it repairs it. Radiation shatters its DNA into hundreds of fragments, but this bacterium possesses repair systems so fast and so accurate that it can reconstruct its entire genetic code in just a few hours. It is, in a sense, biologically immortal in the face of nuclear destruction. These extremophiles are the true protagonists of our hypothetical scenario of invasion. They show us that the alien does not need to be intelligent to be dangerous. It only needs to be resistant. Resistance is the key to traveling between worlds. An organism capable of entering dormancy, surviving the cold of space, tolerating cosmic radiation, and enduring the heat of atmospheric entry would be a perfect candidate for natural panspermia. If we combine the heat resistance of bacteria living in volcanic vents, the vacuum tolerance of tardigrades, and the DNA repair abilities of Deinococcus, we begin to imagine the outline of an extraordinarily resilient organism. And notice something important. We do not need to invent anything from science fiction. Every one of these traits already exists in the biology we know. Evolution in a harsh cosmic environment could, in theory, combine them into a single organism. For human biology, evolved in the relative safety of Earth's cradle, encountering such an organism would be like facing a tank with sticks and stones. Our white blood cells destroy invaders using chemical weapons, peroxides, digestive enzymes, bursts of heat. But what would those weapons do against a cellular wall evolved to resist sulfuric acid? What would our fever, raising body temperature by a few degrees, do to an organism that thrives near boiling water? The existence of extremophiles removes the idea of alien biological invasion from pure fantasy and places it into the realm of biological plausibility. They reveal that the habitable zone is a relative concept. For us, space is death. For them, space might simply be a long, cold road. As we observe these masters of survival, we begin to understand that life is far more stubborn than we once imagined. Life does not ask permission. It occupies spaces. It clings to rock, ice, and metal. And if it can cling to the exterior of a rocket or the surface of a meteor, then the barriers between worlds may not be walls. They may be oceans, vast, silent oceans that patient travelers can cross simply by drifting. This resilience brings us directly to the next piece of our puzzle. If life can survive the journey, how does it hitch a ride? How does it leave one planet and reach another without building a spacecraft? The answer may already be written in the rocks that fall from the sky every day above our heads. Nature has its own space program, and it has been operating for far longer than NASA. Up to this point, we have talked about the resilience of life and about our own biological vulnerability, but there remains a vast gap between those two realities. A gap filled with vacuum, radiation, and distances so enormous that the human mind struggles to grasp them. The question that quietly hangs in the air is simple. How? How could something leave one world and arrive at another? If there are no spacecraft, no pilots, and no conscious intention behind the journey, how could life possibly cross the ocean between planets? The answer does not come from biology. It comes from physics. More precisely, from the violent creativity of the universe itself. To understand how an invisible invasion could begin, we need to look at the scars of our solar system. Picture the surface of the moon. Even in your imagination, you can see it clearly. A pale world covered in craters. If you look at photographs of Mercury or Mars, you see the same pattern. Everywhere, the marks of ancient collisions. Our solar system is and has always been a cosmic billiard table where rocks of every size collide at unimaginable speeds. For a long time, we saw these impacts only as events of destruction. An asteroid strikes a planet, releases enormous energy, kills everything nearby, and leaves behind a crater. End of the story. But physics adds another chapter to that story. When a large asteroid strikes the surface of a rocky planet, like Mars or Earth, the energy released is colossal. It is millions of times more powerful than any nuclear weapon humanity has ever built, and that energy must go somewhere. Part of it melts rock, part of it vaporizes the ground, but a fraction of that energy does something extraordinary. It ejects debris. Chunks of the planet's own surface are blasted upward with such violence that they escape the planet's gravity. They are thrown beyond the atmosphere, into orbit, and eventually into deep space. At that moment, something remarkable happens. A piece of ground becomes a natural spacecraft. And if that piece of ground contained life, this is the foundation of a scientific idea called Panspermia, and more specifically, lithopanspermia, the transport of life through rocks traveling between worlds. This is not science fiction. It is celestial mechanics. We know as an established fact that rocks travel between planets. Scientists have discovered meteorites on Earth that originated on other worlds. By studying their chemical composition and the gases trapped inside them, researchers have identified stones that were once part of Mars, pieces of the Moon, fragments of the asteroid Vesta. These rocks were blasted away from their original worlds by ancient impacts. They wandered through space for millions of years, orbiting the Sun in silence until eventually their paths intersected with Earth's orbit. Then gravity pulled them down. They fell through our atmosphere and landed on our planet. This proves something fundamental. Material moves between worlds. The bridge exists. The road is open. The only question that remains is about the passengers. Imagine one of those Martian rocks before it was launched into space. Inside its microscopic cracks might have lived colonies of extremophile bacteria, like the ones we discussed earlier, perhaps spores of resilient fungi. When the impact occurred, the rock was blasted outward. The outer layers may have been scorched, but the interior, protected by thick mineral walls, could have remained relatively cool. the rock becomes an ark, a biological time capsule. Out in the vacuum of space, the journey begins. It may last months, years, or even millions of years. For a human being, such a journey would mean certain death. But for a dormant spore, time has little meaning. It does not need food. It does not need air. It does not age in the same way. It simply waits. The rock shields it from the worst ultraviolet radiation of the sun. The cold vacuum preserves its delicate chemical structure. It becomes a sleeping traveler drifting through darkness, waiting for a single condition: a new home. Science offers another fascinating clue that enriches this reflection. When researchers analyze ancient meteorites, such as the famous Murchison meteorite which fell in Australia, they do not find living organisms, but they do find the building blocks of life. Inside those stones, scientists discovered amino acids. Amino acids are the fundamental molecules that form proteins. They are the letters of the biological alphabet. Finding amino acids in a rock that came from space is like discovering scattered Lego pieces in a desert where no toy factories exist. It tells us something profound. The chemistry of life is not unique to Earth. The universe itself is capable of producing the ingredients. Inside clouds of interstellar gas, within frozen asteroids, chemical reactions quietly assemble the molecules that life depends on. If the ingredients exist, and the rocks travel between planets, then the idea that complete life might travel as well is no longer magical. It becomes a question of probability, a numbers game. If billions of rocks have been exchanged between planets across billions of years, then only one needs to carry a viable biological passenger for contamination to occur. This perspective changes the entire meaning of the word invasion. We usually imagine invasion as an act of conquest, something planned by an intelligence drawing maps and strategies. But panspermia suggests something very different: an accidental invasion, a biological contagion carried by chance. It is like the wind carrying pollen from one meadow to another distant field. The flower never intended the journey. The wind had no plan, yet the new field becomes colonized. Now imagine that happening on Earth. A wandering rock enters our atmosphere. We see a shooting star streak across the sky. We admire its brief flash of light. The heat of atmospheric entry is intense. The surface of the rock melts and glows like a miniature sun. But physics tells us something important. That heat is brief, and it affects only the outer layers. If the rock is large enough, its interior may remain cold enough for life to survive. Eventually, the rock strikes the ground, or splashes into the ocean. It fractures. Rainwater or seawater seeps into its cracks, and the spore that slept for 10 million years during its journey between planets suddenly senses something it has not felt in ages. Liquid water, warmth, nutrients. Its chemical sensors awaken, and the oldest process in the universe begins again. Awakening, replication. One cell becomes two become 4, then 8, and so on. The most unsettling part of this hypothesis is not only the possibility that it might happen one day, it is the possibility that it may have already happened. Some scientists ask an even deeper question. What if we are the invaders? What if life on Earth did not begin here? What if our planet, once sterile and empty, was seeded billions of years ago by rocks from another world? There is a real scientific debate about this possibility. If it were true, then every living thing on Earth, from trees and whales to you and me, might ultimately descend from microscopic travelers that fell from the sky. In that sense, we might all be Martians. But even if life did begin here, the process does not stop. The sky remains open. Rocks continue to fall. Every year, tons of cosmic material enter Earth's atmosphere. Most of it is sterile dust, but the cosmic lottery never stops running. This form of contact does not require alien technology. It does not require faster-than-light travel. Rocks are patient. They do not care how long the journey takes. The only ingredients needed are resistance and chance is the most persistent force in the universe. If panspermia is possible, then protecting Earth is not only about watching for radio signals or alien spacecraft. It is about understanding that our planet is not sealed. Earth is part of a much larger cosmic environment. It breathes the same dusty air as the galaxy around it. And within that dust, the biological stories of other worlds may be drifting quietly, dormant, waiting for a warm and wet place where they can continue the story that began under another sun. But is this only theory? Can life truly endure the brutality of space, or is this merely the dream of optimistic biologists? To answer that question, scientists have already begun performing real experiments beyond our planet. We have exposed life directly to the vacuum of space. We have turned orbit into a laboratory, and the results of those experiments, performed on the outside of the International Space Station, have begun to blur the line between the impossible and the plausible. That is where we will go next. Now let us leave behind the theories about ancient rocks and travel to the present, to a place where the boundary between Earth and the cosmos becomes visible, tangible, and constantly monitored. In your imagination, rise now into orbit around our planet. About 400 kilometers above our heads floats the International Space Station. It is the most complex structure humanity has ever built in space, a shining laboratory of silver metal moving at extraordinary speed, completing a full orbit around Earth every 90 minutes. Inside the station, astronauts live in a carefully controlled environment. The air, temperature, and pressure are regulated to resemble the comfort of Earth's surface. They eat, sleep, and work, protected by layers of aluminum and Kevlar. But just a few centimeters beyond the walls where they rest lies an environment of absolute hostility. Outer space does not forgive. There is no air to breathe, no pressure to keep water in liquid form. The thermal cycle is brutal. When the station faces the sun, its outer surfaces heat up to nearly 120 degrees Celsius. 45 minutes later, when it passes into Earth's shadow, the temperature plunges to around 150 degrees below zero. It is an endless cycle of freezing and boiling that repeats 16 times every single day. And there is something else. Radiation. Ultraviolet radiation from the sun, unfiltered by Earth's atmosphere, strikes the station directly. This invisible light is powerful enough to break apart the chemical bonds that hold DNA together. At first glance, this seems like the last place in the universe where life could survive, a perfect biological desert. And yet human curiosity asked a bold question. What if it isn't? To answer that question, scientists decided not only to observe space, but to place life directly into it. Over the past decades, space agencies have conducted a series of remarkable experiments. Special containers called exposure facilities were mounted on the exterior of the International Space Station. Inside these small chambers, scientists placed samples of terrestrial life, bacteria, fungal spores, seeds, even tiny microscopic animals. The idea was simple: expose life directly to the vacuum of space and see what remains. These containers stayed outside the station for months. Some remained for years. They endured thousands of cycles of sunlight and darkness. They faced solar storms and deep, freezing shadow. They were bathed in radiation and vacuum. When astronauts eventually retrieved those containers and brought them back to Earth, scientists opened them expecting to find only death. They expected shattered cells, broken DNA, nothing but the remains of life. Instead, they found something unexpected. Many organisms had died, of course. Space is genuinely brutal, but some had survived. Certain bacteria, such as Bacillus subtilis, revealed a survival strategy that seems almost like a military tactic. When exposed to hostile conditions, these bacteria did not attempt to keep living normally. They shut themselves down. They formed extremely resistant spores around their genetic material. Their metabolism slowed almost to zero. They entered a state of deep dormancy, so deep that it becomes difficult to distinguish between life and stone. But the most fascinating discovery came from how these microorganisms survived together. The bacteria exposed directly to sunlight died almost instantly, but their dead bodies formed a protective layer. That layer became a microscopic shield, blocking harmful ultraviolet radiation. Beneath that sacrificial crust of dead companions, the bacteria below remained protected. They survived. Death itself became insulation. When those surviving bacteria were returned to Earth and placed in a petri dish with water and nutrients, something remarkable happened. They woke up. They resumed dividing and living as though nothing unusual had occurred. They had traveled through the vacuum of space and returned. This is not speculation, it is experimental evidence. Life from Earth has already proven that it can survive the vacuum of space for extended periods of time. And if organisms that evolved on a comfortable blue planet can endure such a journey, we must ask an uncomfortable question. What about life that evolved in harsher environments? These experiments strongly support the mechanism we discussed earlier, Panspermia. They show that space is not a perfect quarantine barrier between worlds. It is a filter, a harsh filter certainly, but one that the most resilient organisms can pass through. There was also another intriguing observation. During routine inspections outside the station, Russian cosmonauts collected samples from the surface of windows and solar panels. In those samples, scientists discovered traces of marine plankton and bacteria. The most accepted explanation is that powerful atmospheric currents, possibly driven by storms or hurricanes, lifted microscopic life from Earth's oceans into the upper atmosphere, where it eventually adhered to the station. Even if that explanation is correct, the implication is astonishing. It means Earth is constantly leaking life into space. Our planet is surrounded by a faint biological halo, tiny fragments of life drifting upward, carried by the dynamics of our atmosphere. In our thought experiment, we can look at this phenomenon from another perspective. If one day a robotic probe returns from Mars or from the icy moons of Saturn, bringing samples of rock and dust back to Earth, we can no longer assume that any life present would die during the journey. We now know that life can endure such a journey. The container does not need to be perfectly sealed. Life itself can become the container. This realization has forced scientists to rethink the protocols for planetary exploration. When we send robotic missions to Mars, we sterilize them obsessively. Every component is cleaned and heated to eliminate microorganisms. Why? Because we fear contaminating Mars with Earth's life. We fear that our own bacteria could survive there and interfere with future discoveries. In other words, humanity officially recognizes that biological invasion between planets is possible. So now imagine the reverse scenario. If it is possible for our microbes to contaminate Mars accidentally, then it must also be possible for alien microbes to contaminate Earth. Nature does not create one-way doors. If the path exists in one direction, it exists in the other. Picture a future mission bringing Martian rocks back to Earth. A robotic arm collects a sealed capsule that has traveled millions of kilometers. It appears perfectly secure. But what if, in the microscopic dust on its exterior, in the hinges of its metal joints, something tiny managed to hitch a ride? Something that survived the cold, the vacuum, and the radiation, just as Bacillus subtilis did in orbit. That organism would descend through our atmosphere. It might escape into the environment unnoticed. And here on Earth, it would encounter something it might never have experienced before. Abundance. Liquid water everywhere. Carbon. Oxygen. Stable temperatures. For an extremophile accustomed to fighting for every molecule of energy on a harsh world, Earth would not merely be a new habitat, it would be paradise. And here lies the quiet danger of simplicity. Complex organisms, plants or animals from another world, would likely struggle to survive here. They would require precise conditions, but microorganisms are different. They are flexible chemical machines. They need very little. In a planet rich with nutrients and with no natural predators adapted to them, their reproduction could become explosive. The experiments in orbit have taught us something essential. Life is stubborn. It can shut itself down, drift through the void, and patiently wait for the moment when it can wake up again. And Earth, with its oceans and warmth, is the perfect place for that awakening. As you imagine the space station floating silently above the planet, consider the irony. We built that structure to look outward, to search for answers in distant stars. Yet one of the most important answers may already be clinging invisibly to its outer walls. Life is not something that easily stays in one place. It spreads, it travels, and sometimes it survives journeys we once believed impossible. Now that science has shown us that survival in space is real, the final question remains. What would happen when such life finally meets the complex, interconnected biosphere of Earth? What happens when the invisible visitor meets us? To explore that possibility, we must descend again, from orbit to the surface, and imagine the first quiet day of contact, a day with no explosions. Only subtle changes, changes that might begin so gently that no one notices them at first. Now let us return to the ground beneath our feet. Let us imagine the moment after the barrier between worlds is quietly crossed. We have already seen that life can endure extreme conditions, that rocks travel between planets, and that the vacuum of space is not an absolute barrier. Now, in this guided exercise of imagination, we can picture the moment when that barrier finally breaks. What would day zero look like? Unlike the dramatic scenes in films, there would be no global broadcast interrupting television signals, no emergency meetings of world leaders in underground bunkers. Biological contact is, by nature, intimate and invisible. It would likely begin somewhere remote, perhaps in a dense forest where a meteorite landed unnoticed, or on the surface of the ocean, where a microscopic capsule dissolved quietly in the foam of the waves. To understand what happens when an organism enters an ecosystem unprepared for it, we do not need to look to the stars. We only need to look at our own ecological history. Earth itself is a laboratory of biological invasions. We call them invasive species. Think of rabbits in Australia, or zebra mussels spreading through rivers and lakes. When these creatures were transported from their original homes to new environments, they did not arrive with weapons. They arrived carrying nothing more than their natural biology. But in the new environment, something important was missing: enemies. In their native lands, rabbits had predators. They had diseases. They had competitors that kept their populations under control. In the new land, those checks did not exist. The balance of nature did not apply to them. And without those natural breaks, reproduction exploded. The invader consumed resources, displaced native species, and reshaped entire ecosystems. Now imagine this scenario expanded to a cosmic scale. If an alien microorganism arrived on Earth, it would be the ultimate invasive species. On this planet, nothing would have evolved to consume it. No terrestrial virus would know how to infect it. No microbe would know how to compete with it. The microscopic web of predators and prey that normally regulates life on Earth would have no instructions for dealing with it. Biologically speaking, it might have a free pass. If that organism found a usable energy source, perhaps organic carbon, perhaps minerals, perhaps even something unexpected like plastics or metals, it could begin reproducing rapidly. The first consequences might not be human illness at all. Instead, they might appear in the environment. Imagine an alien microorganism spreading through the oceans and subtly altering the chemistry of the water. Perhaps it consumes oxygen and releases another gas. Perhaps it changes the color of the sea slightly, or affects the balance of microscopic plankton. The changes would not be immediate. They would be slow, gradual, atmospheric. At first, they might appear only as strange data in scientific instruments, climate models that suddenly stop working, chemical readings that no longer match expectations, a shift so subtle that the human body might not notice it at first. But what if the contact were direct? What if human biology itself became involved? Here, our own history provides a sobering example. Humanity has already experienced biological catastrophe, not from the stars, but from contact between civilizations. When Europeans crossed the Atlantic centuries ago, they did not bring only ships and weapons. They brought their bodies, and within those bodies traveled invisible passengers, viruses like smallpox, measles, and influenza. For Europeans, these diseases were old enemies. Their immune systems had centuries of experience dealing with them. But for the indigenous populations of the Americas, those viruses were completely unknown. Their bodies had never encountered them. There were no keys for those biological locks. The result was not a battle, it was collapse. Entire societies were devastated, not by steel blades but by fever. Historians call this phenomenon virgin soil epidemics, diseases introduced into populations that had absolutely no previous exposure. This historical tragedy provides the closest model we have for a potential extraterrestrial encounter. The difference lies in the scale of isolation. Europe and the Americas were separated for thousands of years. Earth and any other world have been separated for billions. The immunological gap would be immeasurable. In such a scenario, doctors might become the first investigators. Hospitals could begin noticing strange patterns. Patients arriving with symptoms that do not match any known disease. Perhaps persistent fatigue that no virus can explain. Perhaps unusual chemical changes in the blood. Perhaps neurological disturbances without visible damage in brain scans. The greatest fear among astrobiologists is not necessarily a dramatic virus turning humanity into monsters. The real concern is something more subtle: toxicity. An alien microorganism might not even attempt to infect human cells. It might simply release a metabolic byproduct, an enzyme, a gas or a molecule that is harmless to it but poisonous to our biology. It would be like slowly introducing an unfamiliar chemical into the air of the entire planet. Another possibility could be even stranger, a molecular mimic. In biology, we already see molecules capable of deceiving cells. Consider prions, the misfolded proteins responsible for diseases such as mad cow disease. They are not alive, they contain no DNA. Yet when they contact a normal protein, they induce it to fold incorrectly as well. A chain reaction of structural corruption begins. An extraterrestrial molecule might operate in a similar way. Not an army attacking the body, but a quiet corruption spreading through the machinery of our cells. Faced with something truly unknown, science would initially struggle. Modern medicine relies on comparison. Doctors diagnose illness by matching symptoms to known patterns. This looks like influenza. This resembles dengue. But a completely unfamiliar biological system would not match any known category. For a time, science would be blind, and during that period of uncertainty, fear would grow. The psychological effect of an invisible threat from the stars would be profound. The sky, which has always been a symbol of beauty, wonder, and inspiration, might begin to feel different. Rain might make people uneasy. Gardens might feel suspicious. The idea of national borders would become meaningless because microbes travel freely on the wind. There would be a tragic irony in such a moment. For decades, humanity has invested enormous effort building weapons designed to fight visible enemies, nuclear missiles, armored vehicles, laser defenses, but none of these tools can stop a spore. You cannot shoot a bacterium. You cannot bomb a pandemic. The greatest vulnerability of our advanced civilization lies in our most fundamental nature. We are biological. We are living systems built from fragile organic cells, and yet history also teaches us something hopeful. Life adapts. After the initial shock of new diseases, survivors develop immunity. Ecosystems find new balances. Over time, what was once catastrophic becomes part of the background of life. If a biological invasion occurred, the question would not be whether life would survive. Life always survives. The question would be whether we would have enough time to adapt. In our modern world, where airplanes connect continents in hours, any biological event could spread globally within days. An extraterrestrial passenger arriving in one corner of the planet could circle the world before we even understood what it was. These reflections are not meant to create fear. They are meant to cultivate awareness. They remind us that protecting our planet is not only a matter of military defense, it is also a matter of biological stewardship. Our biosphere is a delicate harmony shaped by billions of years of evolution, and introducing any completely foreign element into that system carries unknown consequences. Yet, there is another side to this story. Even now, there are scientists whose entire mission is to prevent such scenarios. Quiet guardians who work to ensure that Earth remains biologically safe. Their task is to think about the invisible dangers long before they ever arrive. And it is toward those guardians and the future they are trying to protect that we now turn our attention. After exploring all these possibilities, from the silent resilience of extremophiles to the unsettling idea of microorganisms traveling between worlds, it may begin to feel as though humanity is standing defenseless before a biological mystery written across the stars. But the reality is more careful, more thoughtful, and in many ways more reassuring. While most of us live our daily lives without thinking about these distant possibilities, there are scientists whose entire profession is dedicated to preventing them. They are known as planetary protection officers. This is not a fictional title. It is a real position within major space agencies, such as NASA and the European Space Agency. Their task may sound like something taken from science fiction, but in practice, it is a discipline of extreme precision, strict protocols, and quiet responsibility. Planetary protection exists because scientists recognize a simple truth: exploration carries consequences. Whenever humanity sends spacecraft to another world, there is always the risk that we might bring something with us, and whenever we bring something back, there is the possibility that we might carry something home. Planetary protection works in two directions. The first is called forward contamination. This refers to the possibility that microbes from Earth might accidentally travel to another planet. If that happened, it could contaminate alien environments and destroy the scientific evidence we are trying to study. Imagine searching for life on Mars, only to discover bacteria that actually came from Earth on a previous spacecraft. The result would be scientific confusion on a planetary scale. To prevent this, spacecraft that travel to sensitive environments, such as Mars or the icy moons of Jupiter and Saturn, are sterilized with extraordinary care. Components are cleaned repeatedly. Some parts are baked at extremely high temperatures to eliminate microorganisms. Engineers assemble these spacecraft inside special clean rooms, where the air is filtered more strictly than in surgical operating theaters. Even a speck of dust is treated as a potential biological risk. But the second mission of planetary protection is the one that concerns us most tonight. It is called back contamination. Back contamination refers to the possibility that a mission might bring extraterrestrial material back to Earth, and that this material might contain something alive. This concern is no longer theoretical. Humanity is already preparing for missions that will return samples from other worlds. Right now, robotic explorers on Mars are collecting carefully sealed tubes of Martian rock and soil. These samples are intended to be returned to Earth in future missions, so that scientists can study them in laboratories, with instruments far more powerful than anything that can be sent into space. But before those samples ever reach our planet, engineers and biologists have designed an elaborate system of protection. Imagine a set of nested containers, like a series of protective shells. The Martian rock is sealed inside a tube. That tube is enclosed inside another container. That container is then placed within a spacecraft designed specifically to prevent any direct contact between Martian material and Earth's environment. During the return journey, the sample remains locked away. When the capsule finally arrives on Earth, it will land in a remote desert region. From there, it will be transported to a special facility designed for handling extraterrestrial material. This facility will resemble the most secure biological laboratories on Earth. The air will be filtered repeatedly. Pressure systems will ensure that nothing inside the laboratory can escape into the outside environment. Scientists will not handle the samples directly. Instead, robotic arms operating behind sealed glass barriers will manipulate the material with careful precision. Every grain of dust will be studied. Every possible biological signal will be examined. If anything unusual appears, any sign that the sample contains living organisms, the containment systems will ensure that it remains safely isolated. These precautions may sound extreme, but they reflect something important about science. True curiosity is cautious. The more we learn about life, the more we recognize how powerful and adaptable it can be. Planetary protection protocols are humanity's way of acknowledging that we do not yet understand everything about the universe, and so we proceed carefully. There is another challenge waiting in the future, however. Machines can be sterilized, robotic arms can be sealed inside containers, but humans are far more complicated. Our bodies are ecosystems. Each of us carries trillions of microorganisms on our skin, in our lungs, and inside our digestive systems. We are in many ways living habitats for microbial life. If human missions eventually travel to Mars, and many plans suggest this could happen within this century, the problem of contamination becomes much more complex. When astronauts return to Earth after spending time on another world, they cannot simply step out of their spacecraft and walk home. History has already given us a small example of this. When the astronauts of Apollo 11 returned from the Moon in 1969, scientists could not be completely certain that the lunar surface was sterile, so the astronauts were placed in quarantine. After their capsule splashed down in the Pacific Ocean, they were transferred into a sealed isolation chamber. For several weeks they remained inside, observed by doctors who carefully monitored their health. Only after it became clear that no unknown illness had appeared were they allowed to leave quarantine. The Moon, of course, turned out to be sterile, but Mars may not be. If astronauts one day return from Mars carrying samples, or even microscopic particles clinging to their equipment, they may undergo much more extensive quarantine procedures. Doctors and scientists will monitor them closely. Advanced diagnostic tools will analyze their microbiomes. Every precaution will be taken to ensure that nothing unfamiliar enters Earth's biosphere. There are even deeper ethical questions hidden within these scenarios. What if an astronaut returning from Mars developed symptoms of an unknown illness? What if the safest choice for Earth required isolating that astronaut indefinitely? These are difficult questions. They belong not only to science but also to philosophy and ethics. Exploration always forces humanity to confront the boundaries between curiosity and responsibility. And yet there is also something hopeful in all of this preparation. The effort to protect our planet has led to remarkable advances in medicine and biotechnology. Technologies designed to detect microscopic life on Mars are now being adapted to detect diseases on Earth. Methods developed to sterilize spacecraft have improved surgical safety and laboratory practices. In preparing to explore the cosmos, humanity is also learning how to care for its own fragile biosphere. Planetary protection reminds us that Earth is not merely a launch pad for exploration. It is our home, a living system that has taken billions of years to develop. And preserving that system is one of the most important responsibilities we share as a species. As rockets rise from launch pads and human curiosity continues to push outward toward the stars, scientists remain quietly vigilant. They are the guardians of the invisible boundary between worlds. They work not to stop exploration, but to guide it safely. Because the greatest discoveries of the future will not come from reckless adventure. They will come from patience, from respect, and from the careful understanding that life, wherever it exists in the universe, is both powerful and precious. We have now arrived at the quiet harbor of this journey. The path we traveled together tonight was not measured in kilometers, but in ideas. We began by looking up at the sky with the familiar fear imagined by science fiction. Visions of alien ships and dramatic invasions, and slowly our perspective shifted. Instead of thunder and spectacle, we discovered a universe where the most powerful forces may be subtle, patient, and invisible. As the night deepens around you, and the silence of your room blends with the distant silence of the stars, this is the moment to settle those thoughts gently. Throughout this exploration, we walked along the delicate boundary between possibility and presence. Science has shown us remarkable truths about life. We know that microorganisms can remain dormant in ice for thousands of years and awaken when warmth returns. We know that tiny creatures can endure the vacuum of space and survive radiation that would destroy human DNA. We know that rocks travel between planets, carrying the chemistry of distant worlds across the solar system. These discoveries are real. They reveal that life is far more resilient than we once believed. But the idea of a biological invasion from the stars, the great transformation of Earth by alien microbes, remains for now a thoughtful hypothesis. It is not a forecast. It is not a warning for tomorrow. It is an invitation to humility. Recognizing this difference allows your mind to rest. We do not watch the night sky waiting for catastrophe. We watch it because curiosity is part of what it means to be human. Looking upward is how our species learns, dreams, and slowly understands the universe we inhabit. And there is something strangely comforting hidden within the ideas we explored tonight. If life can travel, if life can survive the cold emptiness between worlds, then the universe may not be a silent desert after all. Instead, it may be a vast ocean where life, simple, persistent, and patient, drifts quietly between distant shores. In that sense, life everywhere may share something fundamental: the desire to continue, to endure, to exist. Human beings often measure success by intelligence, technology, and complexity. We build cities, write music, explore distant planets, and imagine ourselves as the pinnacle of evolution. But the universe may have simpler criteria. For the cosmos, success may simply mean not disappearing, continuing, persisting, remaining. Under that perspective, the smallest organisms, the spores, the bacteria, the invisible travelers, are among the most successful forms of life that exist. They remind us that life itself is not fragile. It is persistent, it adapts, it waits. And if life exists beyond Earth, with the same stubborn resilience we see here, then perhaps we are not alone in a dead universe. Perhaps we are drifting within a fertile cosmos, where the seeds of biology move slowly from star to star. This idea does not need to frighten us, but instead it can remind us how precious our own world truly is. Picture Earth now from far away, a small blue sphere floating in darkness, wrapped in its protective magnetic field, covered by oceans, surrounded by a thin blanket of air that shields every living thing beneath it. Inside that fragile bubble, life has flourished for billions of years. Forests grow, oceans breathe, creatures move, evolve, and adapt. And among them, there are beings capable of asking questions about the universe itself. Beings like you. In this moment, you are safe within that protective world. Separated from the deep cosmos by distance, atmosphere, and the quiet guardianship of nature, the mysteries of life beyond Earth will still be there tomorrow. The questions will remain. Scientists will continue exploring them with patience and care. But tonight, none of those mysteries need to disturb your rest. You are exactly where you belong here, on this calm blue world, breathing slowly, resting peacefully. And before we close this journey, if this exploration of the cosmos helped your mind relax and wander through new ideas, you are warmly invited to stay connected with Cosmos for rest. Leaving a like or subscribing is a simple way to support the creation of more calm scientific journeys like this one. Stories designed to help curious minds explore the universe while drifting into rest. And if you know someone who also enjoys quiet discoveries beneath the stars, sharing this video can help our small community of listeners continue growing. For now, though, nothing more is required of you. The universe is vast, but in this moment, your place within it is calm and secure. Let your breathing slow, let your thoughts grow quiet, and allow the gentle silence of the cosmos to guide you into sleep. Sleep well.